Hello, this is Maths with Lemon, and in this topic we will see the differential equations. Now, an equation which involves a derivative, for example dy over dx, is called differential equation. Differential equations are used a lot to model real-life situations. Examples are rates of growth, cooling, or rate of expansion of an object like a balloon or an oil slick. In this lesson, we will work on how to solve these equations. Now, it is known that the population growth rate is proportional to the population at any particular time. This means that the larger the population, the faster it grows. Let n to be stand for the number of aliens in a population, and t stand for the time. Now, then an expression for the rate of growth of n with respect to t, to time, is something like that: dn over dt proportional to n, the population. This says a rate of growth is proportional to n, the number of people. As an equation, this can be written as dn over dt times k, constant, times n. Now, this is a first order differential equation. Why first? Because it only involves a first order derivative. I also have second order differential equations when I have second order derivatives. Now, in this lesson, we will discuss only for the first order differential equations. Now, the whole point: how do we solve a differential equation? We have already solved simple ones by integrating. Let's see it. Dy over dx equals 2x plus 4. Now, this dy over dx is also like f derivative of x equals 2x plus 4. So we have seen it already, this one. How do I solve it? I integrate to get y. So basically, integration of the left and the right part. So y will be x squared plus 4x plus c. Don't forget the constant, it's very important in the differential equation. This is the general solution to the differential equation. The constant c can take any value. So there is a whole family of curves that can be solutions. So when the c changes, then I have a different solution. Let's see that. You see, one solution, y equals x squared plus 4x minus 3, plus 0 here, plus 4, plus 7, and I have different differential equations. Now, what do we see here? At any x value, they all have the same gradient, given by, what's the gradient of the second part? 2x plus 4. The general solution of this differential equation is this ray of curves, if you may say. Now, we've seen now before that a differential equation can have an infinite number of solutions. For example, let's see this equation. Dy over dx equals minus 0.5y for all the y's that they are bigger than 0. We can create a whole family of solutions where the gradient of the function is minus 0.5y. Now, at y equals 1, the gradient is minus 0.5 times 1. So, minus 0.5. Here are some possible sections of curves. So now be careful, the derivative is minus 0.5, so basically it goes down. You see, that's the gradient of minus 0.5. For all the values of x's, when y is 1, the derivative is minus 0.5, so it looks like that. At y equals 2, put here 2, substitute, the gradient is minus 1. So here I will see, now the gradient, you see now it's minus 1. I make a small dash here. At y equals 3, it's minus 1.5. All these possible gradients can be joined to form a family of curves. So you see, I combine all of them and I have the family of these curves. These curves are like cooling curves, like the rate at which a cup of coffee cools down. There are many things. They look like exponential curves. Are they? Very important questions. We can see it in the future. Solve this differential equation. Now, this can be solved like before because we have a y on the right hand side. So basically we are coming to the basic way of solving differential equations by separation of variables. Let's see what's happening. I will rewrite the equation so that the y's are on the left and the rest, if there was an x, on the right. So you see, I move y here, so it's 1 over y, dy dx equals minus 0.5. Integrate both sides with respect to x. We know that here dy times dx over dx, it's dy. So basically, I will have 1 over y dy, 0.5 dx. Here, we can use this method also, where we can, instead of differentiating both parts, it's dy over dx equals minus y. Minus 0.5y, sorry. Minus 0.5. Now here, I can move my differential of x on the other side, so make it dy over y equals minus 0.5 dx, and then integrate both parts. It's the same procedure by differentiating both of them by dx, but the important thing is to have together the y's and the x, all the others, on the other side of the equation. Now, so 1 over y, it is my ln y, or absolute value y, equals minus 0.5 x plus c. You should never forget the c, constant. When y is, so now I have y equals e to the power of minus 0.5 plus c. I will separate them, and then I will have y equals a e to the power of minus 0.5x. I substitute e to the power of c by a. Now, this is just the same format as the cooling curves. We looked at the growth and decay. In fact, for any growth or decay problem, the solution to that is where a is any number that it's not 0, which is y equals a to e to the power of